On our previous video, we looked at the oxidative addition reaction, which involves an oxidation of a metal in a particular complex and how that results in the breaking of types of bonds in a specific ligand to form a specific addition process introduced into the specific complex. Now in this video we're going to look at the reverse of that particular reaction, and this is actually called a reductive elimination. Now let's do a little bit of a throwback. Now in this throwback, we know that oxidation is actually focusing on the loss of electrons, which results in an increase in the oxidation number. Like for example, if we have a metal which is M, what happens is that this metal will actually perform the loss of, let's say, 1 electron, and that leads the oxidation number to go from 0 here to 1. So what that results in is that once we have that as +1, we have the opposite of the oxidation. Now the opposite of oxidation is reduction, and this results in the gain of electrons, where we have, let's say, a different metal which we'll call P, for example, and P with a charge of +1 will actually gain an electron to become a neutral metal. So this is going from an oxidation number of +1 to 0, which is a decrease in the oxidation number. Now that we have this particular mindset, we're going to focus mainly on the reduction and how the focus, which is the reductive elimination, is occurring in the organometallic catalyst. So what is the goal? The goal is to form new single bonds, which are actually sigma bonds, when a metal atom in that particular organometallic catalyst is actually removed. So as a result of this, we notice that this type of reaction actually occurs at the end of a catalytic cycle reaction, and this process, which actually introduces the ligands that is being removed for the metal catalyst coordinate, results in a reverse of the oxidative addition. Now let's look at the skeletal equation of this particular process. For example, we have our metal which is P, and P is actually bonding to, let's say, X and also Y. What we notice is that once these perform a specific reaction called a reductive elimination, we actually have a product to be formed where this bond cleaves and the bonding pair becomes a lone pair on that particular metal, and this bond cleaves away here from the metal to the X, and that particular bonding pair then becomes a new bonding pair that picks up this Y. So as a result, our P, which has here a oxidation number of 2, will become P0, and our product, which is our ligand, will have a X with a Y. Now take note here that this Y bonding with the X actually forms a sigma bond, which is a single bond between the two ligands right here. And the ligands we're going to be focusing on is not the likes of alkane, which is these guys with a double bond carbon monoxide, where in here we have a positive charge and in here we have a negative charge, or phosphine. We're not going to focus on these types of ligands here because they are actually neutral when they are in their isolated state. We'll be focusing on ligands that when they are in their isolated state, they are charged. So let's look at a specific type of favorable complex. Is it a trans ligand, which is what we have right here, or is a cis ligand, which is what we have right here. To determine which one is trans, we look at the metal right here, and we notice that this metal has a trans configuration in this particular part, focusing on the two methyl groups right here, while on the other side we have a cis, where the methyl groups, looking at this particular structure known to be a square planar, actually is positioned in the same direction. So what we notice after a series of experiments is that there is no reaction when it involves a specific trans reactant. However, a reaction occurs when you are involving a cis compound. Reason is because this cis is actually performing a concerted formation of the product. A result is the formation of, which is as a result of this bond breaking, and then this breaks here and then forms a sigma bond, and we have our other product. So what is happening is that palladium with a charge of 2 has now in the product a charge of 0, and we form our ethane product right there. Now this reaction is done in the presence of DSMO at around approximately 80 degrees Celsius. Based on this, we can now focus on an example, which is we have this particular reactant here, and we notice that this particular ligand, which is this focus ligand, is configured in a cis position. Therefore, it's going to have a concerted process where you actually perform a reductive elimination process, and what happens is that we have this bond giving its electrons back to palladium, and then this bond here cleaves to form a new sigma bond right there. So as a result, we have our new sigma bond, which is generated right here, and what we take note of is that palladium with a charge of 2 initially becomes 0, which shows that there is a reductive process happening on the metal, and we have an elimination of our main ligand, which is right here. This actually is the last step of an indole synthesis process. So that's about it for this particular video. Hope you're able to understand the connection between a reductive elimination reaction and how it's different from oxidative addition. All the same, stay smart and believe in yourselves.